Hello. So we're making a presentation on determining optimal test functions for the two-level density of L functions. My name is Ela Boldyriew, and I'm from Colgate University.
My name is Fangu Chen, and I'm from University of Michigan.
And I'm Jason Zhao, and I'm from the University of California, Los Angeles.
Perfect. So now that we've introduced yourself, we can look into business. So as we know, the series of this form is a Dirichlet series. The analytical continuation to the sum of the Dirichlet series is the Riemann zeta function. Now, the zeta function is built from primes, as shown with Euler product, and serves as a fruitful solution to the functional equation. Finally, we've reached the extremely helpful Riemann hypothesis, i.e. the trivial zeros, which are even negative integers, and all non-trivial zeros of the function are of the form rho half plus I gamma with gamma real. Now, for cuspidal uniform F, the idea translates analogously along with the generalized Riemann hypothesis, rho F equal to half plus I gamma sub F. And the same results follow immediately. The reason we want to know about the zeros of L functions comes primarily from its construction on primes, so that knowing the zeros, we know the primes. In other words, zeta connects primes to integers. Also, it is an inherent part of the million-dollar question we call Burgess-Witten-Dyer conjecture for elliptic curves.
When we look at many different systems, including zeros of L functions, energy levels of heavy nuclei, and eigenvalues of matrices from some given ensemble, we observe the same type of behavior, and that's where random matrix theory is brought into play. The Katz-Sana conjecture asserts that the distributions of the zeros of some family of the L functions are well modeled by the distribution of normalized eigenvalues of a symmetry group associated with the family. We are going to use this philosophy and study some statistics that will capture what happens at the central point 1/2.
So now, assuming Riemann hypothesis, we have order of log C sub f, low-lying and non-trivial zeros. We say that the following is the test function if it is compactly supported, non-negative, even, Schwarz with mass concentrated at Schwarz class with mass concentrated, and positive is 0. Now, for one level, we know how to measure density of L function of cuspidal uniform F near 1/2. However, doing that in practice is a different story. Hence, we take averages over finite subset of F and obtain the nice integral of R against the test function, with W being a distribution depending on F. If families are nice in the same spectral sense, they converge. We know from random matrix theory that this behavior is dependent on the symmetry group of F. So we can mix up both fields and compare nodes, obtaining the following results for orthogonal, special orthogonal, and symplectic groups. For n-level densities, the results follow. The density formula is known, where phi is even, Schwarz, compactly supported, and with its Fourier transform compactly positive at 0. If F is complete, then we also obtain the integral against test function, this time on Rn with Wn of F being again the distribution. Using the following, we obtain analogous results for weights of orthogonal, special orthogonal, and splitting groups, this time n-level. Note here that the delta is the Dirac delta in its standard interpretation. So now that we have this overview, we can look for the problem at hand. We are interested in the average order and the weighted average order of vanishing at the central point of f of q. So looking at those limits, as you can see them right now, we want to minimize the right-hand side, which is the integral over the psi at 0.
Okay, so the main idea for actually minimizing the right-hand side is that we want to reduce this optimization problem using some algebraic manipulation so that the problem becomes more amenable to some functional analysis. And in turn, through this functional analysis, what we can do is reduce this problem to what is essentially just a differential equations problem. And what Iwanek, and Sarnak, and Jesse Freeman managed to prove was that the one-level optimal test function actually exists, given some constraints on the support of the Fourier transforms for each of the classical compact groups. And so the new results that we have is that, so first of all, there's some restrictions because once you move to higher dimensions, it gets a little more complicated. So instead we do is we study a restricted version of the optimization problem. By restricting instead to a domain of test functions which are products of single variable test functions. And then we fix admissible phi1. And then we optimize over test functions phi2. So the setup is analogous to the one-level densities in which we're optimizing over one variable test functions. And the main result here is that we obtain an analogous setup to the one-level case. And we can, most of the tools that we use in the one-level case more or less follow. And so just to outline what ILS and Jesse Freeman were able to prove, there are three main observations. The first being Achizer's theorem and the Paley-Wiener theorem give a correspondence between test functions and L2. And why this correspondence is important is that what it does is reduces the problem so that it's more amenable to some functional analysis. As some of you might recall, L2 is a Hilbert space. Again, very, very nice linear algebra going on there. And so explicitly the correspondence being that if your test function has Fourier transform supported between -2 sigma and 2 sigma, then you can write the Fourier transform as some convolution of G with its cup for G and L2. The second observation is that by Poncharel's theorem, you have this duality between Fourier transforms and the original functions and integrals. Why this is particularly useful is that because our test functions, again, the Fourier transforms are compactly supported. So what we do is reduce from an integration over the entire real line to an integration over some nice interval. And also, third observation is that the Fourier transforms of our distributions are very, very nice. They take the form of delta plus some kernel, which the kernel M is a real valued even step function. Again, much, much nicer than the original distributions, which are just products of sine and 1/x terms.
The problem can be solved in two steps. The first is to reduce it to a different optimization problem. We define a linear operator K such that given an L2 function G supported on -sigma and sigma, Kg is given by integrating G against the kernel M. Remember that phi hat, the Fourier transform of our test function, is supported on -2 sigma and 2 sigma, and can be written as some convolution. We write out the convolution as integrals, and after some simplification, the quantity we are interested in is equivalent to this functional form R. Then we resort to knowledge in functional analysis. Since our density W is non-negative, we know Rg is non-negative for energy, which gives I plus K is a non-negative operator. On the other hand, we know K is a self-adjoint linear operator, so it has an orthonormal basis with all the eigenvalues greater than or equal to -1. In general, it may happen that -1 is an eigenvalue of K. In this case, the minimal value of R is 0, but we are not in this singular case in our applications. Then by Fredholm theory, there exists a unique function f0 that is mapped to 1 by I plus K. So f0 is determined by an integral equation. With some more work, we can show that such f0 is the minimizer we are looking for, and the minimal value is given by the inverse of the inner product of 1 and f0.
Okay. So there's some challenges over here where ideally what we do want is Fourier transforms with large support. Why is this the case? Well, if you really think about it, if your Fourier transform is supported between -1 and 1, then it's also supported between -2 and 2. So by increasing support, you're optimizing over a larger set, and therefore you get better and better upper bounds. And we also want to look at higher level densities because these give better estimates on the average order of vanishing, particularly for higher average order of vanishing. And again, this is because if you recall earlier, there's some relation to weighted average orders of vanishing. However, there are two main obstructions here. The first being that for small support, you don't really detect these non-constant kernels. For example, for the symplectic group, you have this, what you do have is this characteristic function term -1 to 1. And so if your Fourier transform is supported between -1 and 1, then you don't really see any of this behavior happening. But for larger Fourier transforms, say between -2 and 2, then you start seeing some non-constant behavior, and the functional analysis and differential equations methods start getting a little bit more complicated. Speaking of complicated, the n-level densities, higher level densities, they tend to be much more complicated as seen earlier, because you have the Katsonic determinants, which, as some of you might know, calculating determinants, very, very complicated. And moreover, higher dimensional integral operators, they're not as well understood as single variable integral operators. And so to deal with this, what we deal with is a restricted optimization problem. So first of all, with regards to support, we care about -1 to 1. So we fix the test function phi1 such that its Fourier transform is supported in this interval. And then what we want to minimize is this particular quantity, right? Again, we assume that we can split up our test function into a product of single variable functions. And then what we do is optimize over phi2, such that the support of the Fourier transform of phi2 is between -1 and 1. Again, this is trying to recover the one level situation.
So now that we look at the example, which is 2 sub to u, which is clearly a two-level distribution, if we take a psi arbitrary, we obtain this somewhat complex result, as you can see right here. So natural question is, how can we simplify it? Thus, we take a shortcut, and by some variable renaming, we tweak the optimization problem into the equation of optimization of this integral, but this time over -1/1 divided by psi 2 at 0, with psi 2 being another test function with the transform support within -1 and 1. So exactly, as you can see, the renaming here, the one I was just talking about, is just basically tweaking a little bit the formulas from the previous slide and just using them in there to change the problem into something that it's a little bit more easier to work with, since we're kind of like, we're creating a little matryoshka doll. So we're kind of like shoveling a bigger problem into a smaller one. So by using test function psi 2, we're simplifying the problem, which could be again simplified by using psi 3, etc., etc.
Now we have reduced the two-level problem back to the one-level setting. Remember that by Fredholm theory, the minimizer satisfies some integral equation, and we know the minimum is the inverse of the inner product of 1 and the minimizer. Here, the constant C is from the rescaling in the previous slide. In our actual calculation, we have a little bit of freedom in terms of choosing phi1 and phi1 hat. We use this Fourier transform pair, which is easy to deal with and gives relatively good result. The reason why it is nice to work with is that for all the groups G we look at, the kernel Mx is some quadratic polynomial in absolute value of x.
And so just going back to the previous slides, what we'd have is that if we know that G satisfied this particular integral equation, But the thing to notice is that on the left-hand side is that 1 is constant. So when you differentiate, what you eventually get is just 0. And then what we recall is that m is just some quadratic polynomial in absolute value of x. And so as you might recall from calculus, when you differentiate a quadratic polynomial twice, what you get is constant. And then when you differentiate it 3 times, it just completely vanishes, right? And so that's exactly what happens, right? So let's see what happens when you differentiate under the integral sign, right? So for the order 1 terms, what you get is differentiating twice, you get 2g. When you differentiate twice for the second order terms, what again is 2 times the integral of g, but then there's no x dependence. So when you differentiate 3 times, it just vanishes. So in particular, just like an example, unitary group, we want to find g that obeys this particular integral equation. Again, you have this quadratic polynomial term. And then when you differentiate twice, what you get is this nice differential / integral equation, and you differentiate 3 times because of this integral part is just constant with respect to x. What you eventually get is this nice linear homogeneous ordinary differential equation. And we all know how to solve this, right? The solutions end up being just trigonometric polynomials. But if we assume evenness, then the sign terms actually just disappear, right? So we assume that, and just from previous experience with ILS and Jesse Freeman, it's reasonable to assume that these solutions are even. And so what we get is that g is equal to a times cosine 2x plus c. And just by back substituting into the first 2 equations, what we're able to determine is what exactly a and c are. In particular, we were able to do this for every single of these groups. And these are the results. And then from this, we compute the actual bounds.
So using the optimal G we have computed, we obtain these values for various group G. Remember that the quantity we have calculated gives an upper bound to the weighted average order of vanishing at the central point. And clearly the probability will sum up to 1. So by subtraction, we get some lower bound to the probability for the family to have zeros of order less than 1, less than 2.
So further that we can do. So there's a particular reason why we chose this subscript notation for phi k, right? So first we found the optimal phi 1 or phi 2 for phi 1. And the question becomes, well, what happens when we find the optimal phi 3 for phi 2, right? The suspicion is that this should converge to some kind of local minimum, and ideally perhaps a global minimum. However, unfortunately, when we try to optimize and try to find phi 3 for phi 2, the differential equations method fails because we don't really get a nice quadratic polynomial for the kernel. And so what instead we can do is use Fredholm integration. So recall that we defined this compact operator k, and as it turns out, the solution to whatever that integral equation was is just g is equal to the sum of iterates of this integral operator k. And also another method that we can do is some higher dimensional integral operator theory. But again, this is all kind of hocus pocus. It's not really well understood. But again, it's an avenue of further research. And we'd like to thank, of course, Jesse Freeman and Amanda Kilora-Sarnak for providing their wonderful papers. And of course, we'd like to thank Professor Stephen Miller, our advisor, for his ever so helpful guidance on the summer research. And of course, thank you to the audience for your time. And if you have any questions, again, our email's on the first slide, so feel free to shoot us any questions. Cheers.